So this is kind of a very intuitive idea. Can we put some rigor behind it? This is not proven that it's going to work every time, right? So this is what Riemann, he was a German mathematician in the 19th century. So he came up with this idea. Okay, suppose that we want to integrate a function in an interval a, b, right? So we want to define a partition, what we call a partition of this interval. So it's a set of points x0, x1, x2, blah blah blah, xn, right? Where x0 is equal to a and xn is equal to b, and x1 up to xn are points between those, right? So just like those that we chose, right? So this is a, this is b, and then we have x1, x2, x3. They don't need to be like equally spaced, right? They can have any distance between them. Now in every of this, if we have a function that is bounded in AB, right? So f is bounded, then we have that it will have a maximum and a minimum inside each of these intervals, right? So we have the maximum, the minimum at the interval I, which we call this is the infimum. Well, it doesn't have to have a minimum actually, between x minus 1 and I minus 1 and xi. So in this, for all the values of x in this interval between these 2 points, for instance 1 and 2, we have the value of the function there, right? So the minimum in the first interval is the infimum between x0 and x1, right? So this is the first interval, right? So this is the minimum and this is the maximum, right? The supremum of the function in this interval between xi minus 1 and xi. Right? Okay, so we have the function is going to be between these two values, right? So suppose that the area. Let me try to draw this, right? So we have this, right? And suppose we have these 2 points, xi minus 1 and xi, right? So this is this, right? In this interval, right, the infimum of this is mi, and this is going to be capital Mi, right? So the area here of this rectangle, right? We choose this rectangle as we did before. The area of this rectangle is going to be mi times xi minus xi minus 1, right? And the area of this rectangle, which includes all of this, right, is capital Mi times xi minus xi minus 1, right? So now we can sum the areas, like this is the big area, what we call the upper area, and the lower sum, right? So the upper sum of f with this partition is defined as the sum from I equals 1 to n of mi times xi minus xi minus 1. So the sum of the large rectangles, right? And the lower sum is the same, but with the infimum, right? The small rectangles, right? So what I forgot to say is that this method, obviously, if you think about it, if you have a function that goes below the x-axis, this will count as positive area, and this will count as negative area. Okay, you can see that because we're considering the values, the actual value of the function, okay, and not only the absolute value. Okay, so this is, remember, this is called the upper sum, and this is called the lower sum. Okay, so it's obvious that let me erase some of this. Okay, it's obvious that the lower sum is always going to be smaller than the smaller equal than the upper sum, right? So what Riemann said is like we can refine a partition, okay, by adding points to it. So for instance, we have another partition Q in which we have x0, x1, x2, and then let's call it xn plus 1, for instance, and then we have x3, x4, xn plus 2, and so on until we get b again, right, which is xn origin. So we insert new points in here, right? So partition P, right, is included in this Q, right? So this is a more refined, which we call a refined. Q is a refinement of P, right? Now, if you think about it for a second, you realize that the lower sum corresponding to this new refined partition is going to be greater than the lower sum for the other coarse partition, okay? Because if for instance, if you have this function like this, right, and we have the original partition, let's call it x1 and x, in this case, for instance, x2 and x3, right? The lower sum in the original one is this, right? But now in the new one, suppose we have, let's suppose we have xn plus 1 is here, right? Right, the new lower partition, in this case it will be this, right, plus this. So this area is going to be greater, okay? At least it's going to be equal, but in many cases it's going to be greater, right? If you have more points, then the minimal value in some of the new intervals will be greater than the minimal value before. And similarly, it will be the case that this new the upper sum is going to be smaller than the upper sum for the other partition, right? So this is P, right? And again, because the maximal value in this new partition will have smaller values in some new intervals, right? So then we can say, suppose, well, yeah, and of course, if we have any two partitions, P1 and P2, then we can bind them together or join them together, like say Q is the union of P1 and P2, and now Q is both a refining of both, and so we have that the lower sum P1 is going to be smaller than the lower sum of Q, right? Because this is a refinement, and we have that this is going to be smaller than the sum U, right? The upper sum at the same partition, because that's what by definition, and then this is going to be smaller than the original sum for P2, right, for instance. So we're going to have that the lower sum is always going to be smaller than the upper sum irrespective of the partition, right? So it doesn't matter how you partition this interval, you're always going to have that the lower sum is going to be smaller than the upper sum. And this is summarized like this: the supremum, okay, of the partitions, sorry, the sum of the lower sum for all partitions, it's going to be smaller or equal than the infimum of the upper sum for all partitions, okay? This is what this implies, right? So for any partition that we make, the greatest lower sum among all of them is going to be smaller than the smallest upper sum that we, smaller equal, okay, than the smallest upper sum that we choose, okay? And so this led Riemann to the following definition, which is the integral, okay? And he says a function f that is bounded in closed AB is integrable in this interval if the supremum of L, of the lower sum, for all partitions is equal to the infimum of U between all partitions, okay? So that means that if we get, you know, we get the partition for which we can make the lower sum as great as we can, right? That's the supremum. Has to be equal to the infimum of the upper sums. Okay, that means that this strategy that we have making with the rectangles will coincide. You know, both the upper sum and the lower sum will merge together in the same value, and that value is what we call the integral, right? This integral between a and b of this function f. Okay. Well, we typically, so that was Riemann's notation. Typically use this notation, right? Fx dx, which was Leibniz notation. Okay. So the idea that Leibniz has is that we're summing. So this symbol for the integral is an s, right? This an s for sum. Okay. So we're summing the values of f, right? The areas of rectangles with height f, right? F, and width dx. Okay, so dx, the idea is that it is very, very small x. Okay. So yeah, not all bounded functions are integrable. For instance, you know, typical example of non-integral function is that if we have one, the function that is 1 when x is a rational number, and 0 when x is not rational, well, it's not going to be integrable because the supremum of the lower sum, okay, sorry, the lower sum for every partition, right? It doesn't matter what partition we choose, the lower value of the function is always going to be 0, because in all intervals there's always going to be at least one irrational number, and the upper sum, it's always going to be 1, okay, because in all intervals there's always at least one rational number. So this is true for all partitions. Okay, so the supremum of L is going to be 0, the infimum of U is going to be 1, and so it's not equal. Okay, these two things are not equal. Okay, one example of an integrable but weird function is, for instance, this f is the function 1 when x is 1/2 and 0 when x is different from 1/2. Okay, and in this case what we have is that the lower sum, obviously for all partitions, is going to be 0, right? And the upper sum is going to be, let's say, delta x, okay, where delta x is the value. So this is 1/2, this is 1, right, because that's the value of the function here. Delta x is the width of this interval, right, containing 1/2. Okay, but then we can refine this partition, right, U, by making this, you know, narrower and narrower and narrower until the width around 1/2, you know, the limit of that goes to 0. Okay, so we can take this and go to 0. So the limit, the supremum of L, which is 0, coincides with the infimum of U, which is 0. And so the integral of this function between, for instance, 0 and 1 is 0. Okay.